Thank you, Brian. Hi there, everybody. So I'll be talking about orchestrating confidential compute. First of all, thank you, everybody, for staying so long. And I'm sure our leads, OCP security leads, Brian, Kelly, Jeff, they would be really, they would have been amazed that when we said save security for the last, save best for the last. So on the 4th day, thanks for that. Let's get on with the topic. Yeah. So we're certainly talking about a revolution over here when we're talking about confidential compute, just like we had a revolution when HTTP switched over to HTTPS, when everything became changed to TLS, encryption for the data in transit. Similarly, when we talk about confidential compute, we are moving towards a trifecta, the completion of the trifecta of data and code, while in use also being encrypted. We do ensure CIA, confidentiality, integrity, and authenticity during processing of the data, not only during transit, during rest. The key goal is to make CC ubiquitous, remove them. Friction points, remove performance hits for wider seamless access, and reliable firmware software updates, and then adoption. It helps us to ensure that even against adversarial platform owner which has got compromised, workloads are protected against unauthorized access and exploitation. They cannot access nor can tamper the execution of code and the usage of workloads in the trusted execution environment. We enforce this via hardware-based isolation, via attestation. Examples of, here we show the intersection of technologies which we use. We have an option to use homomorphic encryption. However, homomorphic encryption, as we know, that data while in use needs to be acted upon encrypted data. And that we know, research has proven that that is many magnitudes higher than acting upon unencrypted data. Multi-party computation is a key use case, as Microsoft Azure's Mark Rasinovich has been evangelizing and working on since several years. So I really appreciate that he's been keen to point out that a key use case of CC is multi-party computation, wherein, say, we have got different vendors having different views of data. So they can use their different views. They can submit it to agreed upon code which is executing within a confidential compute environment, and that code can act confidentially on different views of the data and yield better results. Example, different vendors, say a credit card transaction company and a bank. Both of them may have different views of transactions. However, they may not know each other's transactions. So they need not know. They could submit their code, their data, different views of the data to a confidential agreed upon code in a TEE. And that code could analyze it and do targeted ads for customers, and those ads also, those customers' names also need not be known to either of those parties. Hence, multi-party computation will be helped a lot via confidential compute. So we do have data in use isolation methodologies where we do memory isolation, CPU addressability isolation. We have access control validation, address translation, paging control, RAM encryption, and the various hardware-based ARM Trust Zone, CCA, Intel SGX. Those environments allowing us to implement CC. Now we talk about the software components. So as we navigate this slide from left to right, we see that a library, so the dotted reds talk about the confidential computing components. So a library may have a small CC component, whereas a virtual machine may have several others. The processes, the container runtime, the guest OS, the virtual machine itself. That would be under confidentiality. So here I'll be talking about CXL, implementing CC via CXL. Micron is a key. We launched the world's first and second generation qualified Computer Express link modules. So we do work on CXL a lot, and CC is a key work artifact coming up. So here, the reference architecture for CXL confidential compute dwells into detecting TSP support, component measurement and authentication via SPDM, attestation authentication, memory encryption, transport, security, access control, configuration, dynamic capacity devices. So how to interpret this diagram? We navigated from bottom to up. The green portions are the components in the TCB. A portion of the memory on the CXL memory expander, which is a high bandwidth, high throughput, low latency cache coherent protocol. So that target memory is under the TE's TCB. There's a memory controller, the .mem transactions. Through IDE, we encrypt the data during transit. And similarly on the TSM, the T security manager on the host side on a server processor that has its corresponding memory controller, .mem transactions, and host. So we will dig deeper into this. So here in the middle right, talk about IDE, which is used to allow link encryption. There's a memory security engine, the MSE. That state machine is implemented in RTL because this on the data path, as we said, friction needs to be reduced to the maximum for wider adoption to make the use cases more prevalent. So MSE we implement in RTL, the memory controller. We exchange the keys using .mem traffic. Similarly, the device security manager on the component implements cert chain, per part device cert chains. And similarly, on the host also we have that. We'll dwell a bit more over here further on. So we exchange the data using SPDM secure channels, secure messages. Therein we talk about vendor-defined payloads. And these vendor-defined payloads, they could be either IDE. So as we talk about varies, why do we say varies? Because the CXL IDE management message, which could be configuring the keys, which could be exchanging the keys. So it could either be an IDE message, or it could be a TSP protocol, which is analogous to the TDISP. It could be those messages. We'll delve into what is TSP. It acts as a verifier and policy engine, manages trust decisions, remediation mechanisms and methods for, allows for SPDM secure sessions, connections, attestation, allows for managing the device state, configuration, provisioning, encryption keys, and allows for also bringing in CXL switches to the TCB. Since it is transparent, the CXL switch is also transparent to the and it gets added to the TCB. A key point, no pun intended, key point over here is how we enforce it. We have the CXL TSP spec talks about a trusted execution bit, which tracks cache coherence at the cache line boundary, which is 64 bytes. Each 64 bytes will have a TE bit associated with it. And the transaction is initiated by the host, which sets a TE bit during memory allocation or access. And CXL memory devices checks the state of the TE bit before it allows access to that particular memory, which has been allowed for, or which has been allocated for the confidential compute use cases. So only once the TE bit is locked, or that particular memory region of the physical on the DIMM on the CXL memory module that is locked, it allowed access for the host allowed access for rolling out pooling use cases or multi-tenant isolation. And key point being the hardware must enforce T integrity per cache line, especially during cache evictions, silent writes, streaming writes. Key component is our baby, which we have developed in part of the OCP security forum. So secure boot foundational layer, which allows for making sure the OEM's trusted firmware gets executed on the device. It allows for CIA, the optional confidentiality, integrity, authenticity, anti-rollback feature is implemented so that known vulnerable firmware do not get executed in the field. Optionally, a certificate-based trust hierarchy, and we certainly do life cycles, as was spoken about in the Calyptra calls, talks just now. So specifically focusing on the establishing the immutable root of trust, immutable ROM, securely anchoring the root of trust public keys, having a digest of the root key as an immutable anchor in fuses. We have the signatures, verify the signatures. The hashes allow for data integrity. The digital signatures allow for authenticity, measured boot as per the OCP attestation spec. Revocation is also supported using OSAP and UFI. We'll move quickly, 5 minutes. And so RATS architecture is certainly used for generating, conveying, evaluating evidentiary claims. We accept a verified device, and spoken in the last call, I'll not repeat that. SPDM key, how it helps to orchestrate is it allows for a robust device identity management for tenants and CSPs to bind the evidence from the TSM to the DSM within the TSP configurations to allow no man-in-the-middle attacks and replay attacks. IDE, digging a bit into IDE, so we have skid mode, which allows, so talk about CXL IO, which acts upon TLPs, transaction layer packets, and CXL dot cache mem, which acts upon the flit boundary. Here there's a plaintext CRC and a MAC, which gets acted upon. So this 16-byte MAC, this could be in the skid mode, could be after 5 flits, or in containment mode, which is more secure after 128 flits. So that we support. GCM is used, encryption. So a quick overview of how we use SPDM, maintain a primary session between the TSM and the DSM, and then exchange the keys. And the key example being how we enforce this is right from the left. So this is our favorite diagram for a software developer, where we talk about the UML diagram for the timing diagrams. Here, right from the VMM, the virtual memory monitor, to the memory security engine, the request comes to establish a secure session. Then we talk about getting the memory security engine's capabilities. That is responded to by the device. Capabilities responded, configurations are set. That goes all the way to the MSC engine, which could be implemented in RTL. Then the configurations are locked. And once this configuration includes the memory ranges which the device is ready to spare for CC workloads. And so these are the key use cases. We spoke about multi-party compute sharing, weights. While training the data, weights are what is confidential. A DeepSeek or OpenAI may have a lot of the differentiation comes from the weights. So those weights we can use, enforce confidential AI using CC, moving more workloads to the cloud. RAG use cases, we establish a CC environment and then feed in confidential data, say proprietary specs, ask the LLM to retrieve data or analyze it after so using confidential inference. Digital wallets are implemented. Sovereign clouds, we spoke about hardware-rooted trust, the benefit scalable attestation, key challenges being key management, vendor interoperability, integration complexity, and we enforce the trust decisions, orchestration, And call to action would be, please join our OCP security working group, CXL consortium, where we talk about TSP and confidential compute and the OC3 conferences, talk about that, and highly appreciate all the security architects in this room who meet week on week, who have been contributing to all these ingredients to allow for the orchestration. We want to make the CC ubiquitous and solve for the bottlenecks. Much appreciate to my leadership to help motivate contributions. Thank you.
All right, we've 15 seconds if anybody wants to ask a question.